Okay, good afternoon, everyone, and thanks for joining the Informs NCSU Student Chapter webinar series. Today, we have an event joined with the ICGSA as part of the Grad for Grad program. So Kimia, the Vice President of ICGSA, will present a tutorial on R programming for data science. She's now a third-year PhD student in the Edward P. Fitz Department of Industrial and System Engineering at NC State and has received her Master of Operations Research, in particular, from the same university. Her research now is to combine data analysis and simulation to generate some interesting observations. In this talk, she will, in particular, discuss how to implement various regression and classification algorithm, in particular in the R programming language. So actually, before we start off the official talk from Kimia, I'm inviting all of you, the participants, to open your own camera so that we can take a group photo together for this event. Is everybody comfortable with that? I see we're kind of still admitting people. So everybody who has just joined the event, if you feel comfortable, please turn on your video for now. Can you turn on your video for like just half of a minute? Three. All right. All right.
Did you take the photo, Tianchen?
Anybody else who can take? We still have
okay.
You'll have those 4 people who have muted their camera. If possible, I might. Let's take another one. 3, 2, 1, 0. All right. You can start now, Kimia.
Okay. Hi, everyone. I'm Kimia, and thank you all for coming today. So today we're gonna go over some basic programming methods for analysis data and in R. I'm gonna share my screen. Oh, before that, how many of you have RStudio installed on your machines right now? You can use the reaction buttons to just give me an idea. Okay. Alrighty. So I think more than half. So for those of you who don't have R on your machine, I think because I'm gonna go over the presentation slides first, then I'm gonna go to R and we're gonna code together. So if you don't have R installed, I think it's a good idea to install RStudio while I'm going over the presentation slides. It would take around 30 minutes. So you have enough time to download and install it.
We try to capture anything on screen share, or will you share the presentation with us later?
Yeah, I'm gonna show the code there too, but I thought that coding at the same time with me would be better. You will learn more.
No, I was just wondering if you were going to share the presentation as well. That's all.
Oh yes, I was just gonna do that. Sorry, I didn't get that.
Okay.
Okay. So you have access to the presentation files in the Google Drive too, if you wanted that. Okay, let's see. Okay, so today we're gonna talk about data analysis in R. The questions that we're mainly gonna cover today is how to read data into R, how to pre-process and clean the data, how to build linear regression and some other regression models in R. And then after we build the regression, how to make prediction using those models and interpret the results. Then hopefully We're gonna talk about classification models in R and some general ways to find out if a model is the model you built for your data is actually good enough or not. Okay, so the basic RStudio, when you install it, you can see the basic RStudio looks like this. It has 4 different windows. I'm just gonna introduce it now here, and then when we go to the coding part, you can see it there too. So the left top window is the source editor. This is where you basically type in your code, and you can select multiple lines, or like select all of the codes you've written and click run on the top bottom here, or click Control and Enter to run the code. On the bottom, you have the console. Console is basically, this is RStudio, okay? So console basically calls R to run the code you written on the window above. Or you can directly write code into console too, but you wouldn't have you wouldn't be able to edit it or like remove some parts after you run it. On the right bottom, you will see the outputs of your code. If you have any plots or graphs, you can see them here. It also has another tab called Help, where you can type in the name of the functions that you want to see the documentation for, and you can see the explanation in the R documentation file here. And the last workspace is the browser here on the top right, which you can see a list of the objects you created during your programming. Okay, so this is the basic R. Now we can go ahead and start learning some typical commands to reading the data. So the most typical data types that we usually work with is .csv or .data or .text. Or sometimes Excel. So for these two, we have very specific commands. So whenever you open the presentation on your own computers, you can click on these links. There are links to our documentation if you wanted to learn more about them. I'm just gonna mention their basic inputs and their default values. So for the CSV file, which is comma separated vectors, you're gonna use the command read.csv. So the file name is actually the address of the file, which you should put it in the quotation marks. And the default for read.csv is that it assumes that your data has a header row. So you need to be careful a little about that, because the next command, which is read.table, the header default is false. Sometimes I make this mistake every time, so I'm just gonna mention it here, so you know that to be careful of that. So for the next type of the data, which can be either .data or .text, you can use the command read.table. Read.table is more general than read.csv. You can basically read CSV files with read.table if you set the separator to be comma, but since we have a readily command for the CSV files, you don't need to use that for the CSV. Okay, so here's these two most commonly used commands. Then we have the RData data type. RData is basically if you run R and then you build a bunch of data sets there, or you make a model and you want to save that model somewhere, you can save it into a RData data type, and then whenever you wanted to reuse that model, you can use load, then the file name of the R data, and then you can read it back into R. Next, if you have Excel, for that you need external packages. The package you can use for reading Excel file is read Excel, where the command inside that package is read_Excel, and you need to enter the sheet name of the Excel sheet too. Now, These are commonly used commands for reading the data. If you're working with very big data, like if you have, I don't know, more than 2 million rows and 1 million columns, it's not very efficient to use read.csv to or read.table to read that data in, because that can take, I mean, around 15 minutes to read the data in. So for these kind of data sets, it's better to use another package that's called data.table. This package uses parallel processing to read the data in, and it's command. Sorry, I'm reading a question here. Is there support for SQL database connections? Yes, there is. There are some packages for that, but I don't have them in my slides today. So yeah. Okay. So I was saying that you can use the fread command. This is 15 times faster than read.csv, and it will save you a lot of time if you have big data. Okay. So the very most important step of data analysis and data science is how you pre-process and clean the data, because in the real world, the data sets are not that pretty in like matrix form that we always see in our courses. It's usually have like a lot of missing values, a lot of redundant variables there, or like high correlation and this kind of stuff. So we need to clean the data and make it pretty enough and tidy enough for us to build models on. In R, the three main packages that we use to clean up the data are tidyverse, dplyr, and caret. And there are some other packages we can use as part of these to plot the data to make sure that the data we are working on is actually like tidy enough. To install the packages into the R, you can use the command install.packages and then the package name. You can see it inside the if command here that I written. So if I want to be more specific here, I'm checking. You don't need to do that. I just did it for the ease of the coding. So I'm here checking the packages that I've already installed into R using the row names of the install.packages in my machine, and then check if these packages that I want to work on are already inside the installed packages. If they are, then we don't need to reinstall them. So if it only checks that do you have these packages already installed or not, and if yes, it installs them. Then whatever package you have installed into R, you only need to install it once for your R Studio, and the rest of the times you only need to call the package in. And you can call the package using the library command or the require command. They're both the same. For our purposes are the same. They have some specific differences. Okay. So here I'm calling in the different packages that we're gonna use using the library command. Okay, so let's see. Yes, you have to call the packages every time. So you have to run the library, then parentheses the package name every time. Otherwise, R doesn't know which packages you're referring to. So you don't need to install them every time, but you need to call them every time. Okay, so one of the most important packages that we can use is the tidyverse package. This is a collection of packages, actually. If you go to their website, you can see this cute picture that has like different pictures of the different packages that they contain. The most important ones that we're gonna use is a tidyr, dplyr, and ggplot2. Another great opportunity that the tidyverse gives us is a pipe operator, which is percentage, then greater sign percentage. This operator helps you to clean up your data, but instead of just keep calling a function and then putting another function into another function into another function, you can use the pipe operator, which makes all of your functions look linear and more clean, so it's easier to read. For example, if you had log of sine of expectation of 10, you can instead write this as 10, then pipe operator, exponential, then pipe operator, then sine, then pipe operator log. So it goes from the very inside function and goes out. This helps you to have a very clean and structured codes. A list of functions that are very helpful in tidyverse, that it's good to have in your toolbox and know about them in case you need them later on, are listed here. I'm going to go over each of them. So we're going to use some of them later on in the code too, but if we didn't, we just know that you have these options later. So if you have a data set and you want to like select only some of the rows based on a condition. For example, you only want to select rows that does not have any missing values. So you can use this using the filter function, and then inside the filter function you can use the condition you want to filter the rows. Another function you can use is a select. Select does the other way. So it selects the columns instead of selecting the rows. You can again select a list of or a vector of column names here. Another thing that is really good, and if you have ever worked with database management, you probably use it a lot, is the group by function. The group by groups the data rows based on the different values of a variable name, of a variable. So for example, if I have a variable of gender and then I have like male and female, the group by creates two different data for me, one for females and one for males. And this is actually very helpful if you want to summarize that groups in some way later on, which you can do it by using the summarize function. So after you run the group by, you can run summarize onto after the grouped data, and it can summarize the data for you. For example, you can compute average within that group or the standard deviation within that group, and you can analyze the data. These two functions are mostly helpful if you're doing explanatory data analysis and you want to like see what the data is telling me without actually building machine learning models on it. The next very helpful function is the muted. Muted is used for creating new variables. There are other ways to create new variables, but if you want to use a function from tidyverse, you can use muted, and you can add the new variable name and then the function of the old variables that you want to add. And another function is transmute. The difference is actually the same as the muted, but the only difference is that transmute deletes the old variables after the new variable is created. Okay. So I know this was really fast, but I just wanted to let you know that you have these options if you wanted to use them. Okay, so let's go through a pre-processing checklist that we should always have in mind whenever you're working with a new data. So the very first thing to work with, if you have a table or data, is to check for the missing values. So missing values means that when, for example, the operator that was collecting the data missed some of the points, or like for some days we don't have the data, we don't have any data points for those days, but we have the rows for them. So we don't necessarily have any numerical values for those cells. Now, to check if the data has any missing values, you have two functions you can use. Either use any NA. Any NA takes in the data in and returns a single logical true or false. whether the data had any NA values in it or if they didn't have any NA values. The other function you can use is is.na, and this function is returning, it takes in the data and returns another data where each element is replaced with either true or false, meaning whether that specific element was missing or not. This is.na is helpful if you want to see, for example, for each column, how many missing values I had. So you can you can save the is.na of a data, and then you can compute the column sums, because R considers trues to be 1 and false to be 0. So when you compute the column sums, you can get how many missing values per column I have. Or you can compute row sums to see how many missing values per rows I have. Now, when you have missing values, there are some options, there are some stuff you can do with it. If there are very few missing values there and your data is already big enough and you don't need to worry about the missing values, you can easily remove them using na.omit here. Or if you have some columns that have like most of their values are missing, probably those columns are not going to be so much informative for us into the modeling either. So you can remove those columns specifically. Or yeah, the NA, or if there are like some rows that have like missing values, for example, some days you don't have any data recorded for them, you can only remove those days or those rows. There are a lot more ways you can deal with missing values, and these are just like very, very basic ways you can deal with the missing values. But I think for the purpose of having like a regular data with some missing values, these are enough to deal with them. So if you don't have like any of these, if you don't have any of these options I said, you can replace each missing value with the median or the average of its column, removing the missing value. So you can use the mutate function that I said in the previous slides and replace the variable with replace the missing values of that variable with the median of the whole column. Okay, so the next thing that we need to check for our pre-processing is to check the data and the column types of the data. So you can check this using function glimpse. Glimpse is inside the tidyverse package, or using the basic function summary. They both return you a list of the variables you have in the data, some of their values, and then the data types. So we're gonna see these in our codes. So you can use these two functions to check the column types. Now, for our modeling, for the linear regression or our classification models, we need all of the values of the data to be numerical. Now, if you have categories, there's no problem. You can convert them to numerics. Now, for example, if you have a column like marital status, which has like 3 categories here, you can convert this into another matrix where each column represents each value of the categories. So marital status single only takes 1 if the category was 1 here. If the category, was single here for the marital status. But the thing you need to notice here is that if you convert for each value of the categories in a column and create a binary vector for it, you would get a redundant column, because, for example, in this example, the MS divorce only takes 1 if the single and married are 0. So I can already tell what value the third column would have without even seeing it. So that's why one of the vectors that you create is going to be redundant, and you need to drop one column at the end. You can there are some functions that does this for you. You don't need to do it by hand. You can do it by hand. It's not that hard, but there are some functions that does that. The function that we're gonna use is called dummy vars. This is inside the caret package. What it does is that it takes in the data with the categorical values in it, and then returns a model that that creates these binary vectors for you. You need to set the full rank equals true to tell it to drop those redundant columns at the end. Sorry. Yeah, okay. So the next thing that you need to check in your data is to see if your variables have near zero variances. So to do that, you can either check the variance of each column separately and then check the values of the variances, see if some of them are very close to zero or are actually zero. Or you can use another function inside the caret package, which is near zero var. It computes the it actually gives you a list of the columns that are considered to have near zero variance. What it does is that it checks the frequency between the most frequent value of the column. Sorry, it computes the ratio of the most frequent to the second most frequent. If it's more than 95 to 5, if it's less than 95 to 5, it's fine. If it's more than that, it returns it as the near zero variance. Another thing that it checks is the unique cut, which is it computes the percentage of the unique values you have in that column. So basically, it gives you a list of the variables that does not have enough variability in them to be informative. Now, you can either group these variables together to make another variable that has more variability into it, or you can delete those variables altogether. It depends on the case. So we're going to see an example of this in the data too today. Okay. So next, what we need to do is to check for the high correlation between the variables, because most of the regression models and linear classification models that we're going to see later, they assume that the columns are independent of each other. So we need to make sure that they're not highly correlated to mislead the model later on. So to check the correlation among every variable, you can use the function core. And the method here, I'm going to use Pearson, but there are 3 other methods that you can use. You can check the documentation here if you wanted to learn more. Now, if you have a lot of variables, this core function might not be so useful because it does not actually go ahead and compute each of them. And it computes a value and tells you, okay, these 2 variables had high correlation. You have to check it by hand, and it's not that easy. Instead, you can create a plot using this correlation matrix. And I usually plot a heat map that is dark blue if it's highly correlated, positively highly correlated, or if it's dark red if it's negative and highly correlated. We're going to see how to plot these heat maps later. This is one way. Another way is to write a function your own and go ahead and check every row of the correlation matrix and find the highly correlated values, and then return the names of the rows and the columns for that. We're going to see both of these examples in the code. I think, yeah. Now, the last step for your pre-processing is to see if you have very like if your data has a lot of variables, like I don't know, a lot, more than 100, and there's a good chance that not all of those variables are useful to you. There are a lot of redundancy or noise variables there that you need to identify. There are many methods that you can use to select the actual real variables from a data. Some of the methods that we're going to cover today is the forward and backward selection, which starts with all of the variables and starts dropping each variable at a time until it sees until it doesn't see any improvement in the mean squared errors. There are other criterion-based selection methods like AIC and BIC. These compute the amount of the variability that is explained using the model with these variables versus another set of variables. We're not going over to the details of these criterion-based selection methods. What we're gonna see another method that's called regularizations. Regularizations are also for those data sets that have a lot of variables. A very famous example of a regularization method is the Lasso regression model. Lasso, we're gonna go over the formulation for it, but Lasso, what it does is that it adds a penalty to the loss function that it's computing the best variables in the data, and based on that penalty, it selects the best variables. Okay, so after these, we are good to go. We have a clean data that does not have any highly correlated variables or missing values, and it's good to go. Now, before we go to regression and classification models, let's talk about what is the difference between supervised and unsupervised learning methods. So we have two general learning algorithms in machine learning. One is supervised, the other is unsupervised. The supervised has the data, which is X, in addition to a vector Y, which is what we want to predict, what we are interested in to finding out the relationship of Y and X here. So Y is usually called the response or dependent variable because it's dependent on X. We want to find the relationship between them. And the model is going to see a sample of X and Y when it's training the algorithm. And it's also going to see, it's only going to see another set of X later to predict the Y values for them. So for supervised, the model sees the response and the dependent variables, which are our X's. For the unsupervised, you're not interested in predicting any response variable. You're only looking at a data without any response, and you want to find the relationship between those data itself. For example, you have a lot of data about about customers you have, and you want to find out what are the groups inside those customers that you can separate. And you're not actually predicting anything. You're not predicting the sales for those customers. You just want to separate those groups of the customers. This is called unsupervised learning because it doesn't have any response value to look at. These unsupervised learnings are usually a lot harder, and their application is not as commonly used as supervised learning. Supervised learnings, usually models have the advantage of seeing the Y, and it can build a better connection between Y and X. Now, if the response variable inside the supervised learning is quantitative, we call it regression. If it's not quantitative, we call it classification. An example for regression is house prices. For example, you want to predict the house prices for the next season, I don't know about anything about the house price. I just made up that example, but those real value response is going to be the regression for you. And if you had different kinds of categories to predict, for example, whether a patient is going to live or die. So this is only 2 states, and this is a classification model. Yeah, we're gonna see examples of both of them today. Okay, so how to build linear regression models. So for linear regression, it's as simple as it can get for a model. It's you have y and you have different x's. Now you want to build a linear relationship between y and x, which is simply a matrix inversion. So what it does is that it takes in the data and it inverses the x's for that data to compute it inverses the x and then multiply it by a bunch of other matrices, and then it gives you an estimate for betas. So betas here are our parameters where you can build a linear function using those betas and different x's to predict the y. In R, it's a simple command you can use for building this model. It's called LM, linear model. And then you can use, and this function here can be represented by y tilde dot if you want to use all the variables inside the data, or y tilde different variable names that you have on the right. Now, another simple algorithm, simple model that you can build is a polynomial regression. And it's not that much different from the linear regression. You just have replaced, like, for example, if x2 here was x1 squared, then that would be a polynomial like regression. The only thing that you need to be aware of when you're using a polynomial regression is that when you add those square terms or like interaction terms, you need to normalize them before you multiply them or add the power to them, because they're going to be highly correlated to other variables if you don't normalize them, and it would have high variance. They would have high variances with respect to other columns, and your model is going to give you NAs as the parameter estimates if you don't do that. Okay. Now, linear regression has 4 important assumptions in mind that you need to check before you make any prediction using that model. The 4 assumptions are, the very first one is that there is a linear relationship between x and y. You cannot always 100% check that. What you can do is that you can check the scatter plots between x and y and see if there is like a very obvious nonlinear relationship there that you need to account for. For example, if the scatter plot looked something like this here, you know that this is not linear. So you can add the 3rd degree polynomial to the model to make sure that you're actually accounting for the underlying relationship there is between y and x. Okay. Now, the next assumption is that it assumes that all the data points are independent of each other. And to check this, you can check the scatter plot between the residuals. Residual is the difference between what you predicted for y and what was the actual y. So that difference is called residual. So you can plot the residuals versus the fitted values of the response, and if there are some dependency, you can see like there are some relationship, some polynomial relationship. They're not independent. If they're like randomly scattered along the axis 0, then they're independent. This is one way to check. The next assumption is I never can pronounce this. Homoscedasticity. Oh, I think I nailed it. That is actually a fancy word for constant variance. So you need to check that the variability around the axis, the zero axis you have for the same plot. I'm talking about the same plot, residual versus the fitted value. The variability across the x is not different. Like, for example, they don't look like something like this. They're always like this. So this is one way to check. They are the simplest way to check these assumptions. So there are some numerical ways to evaluate them, but we're not going to go into them because they need more theory behind them. Okay, and the last assumption is the normality of the error terms. So these error epsilons here, we assume that they have normal distribution with a constant variance and average 0. So you need to make sure that they're actually normal. And you can check that using a QQ plot, which is quantile plot. And on the y-axis, there are quantiles of the normal distribution, and on the x-axis, the quantiles of your data. And it checks if they lie across the 45-degree line. If they do, then your data is actually having a normal distribution. Okay. So after you build the model in R, you can you can compute the estimates of the coefficients. R gives you something like this. This is the output of the R. I'm going to show you how to make it a lot prettier, but right now let's have this. So what it tells you is an estimate here for each coefficient, and also their standard error and the p-values. Now, p-values tells you that whether that estimate is actually significant, statistically significant, and it's not equal to 0, because depending on their standard error, they might be very well centered around 0, where 95% of the times they're no different with 0. So this p-value actually tells you if they're different from 0. If they have star in front of their p-values, that means they are significant, and you can use these estimates. So one way to interpret these results is using these coefficients. For example, if you want to evaluate the V3 here, you can say if we keep every other if we keep every other variable fixed, then we add V3 by 1 unit, then the response, or V1, will increase by 0.01. So this is how you interpret them. If you had interaction terms, you can also interpret them as keeping everything else fixed, only having those two variables in the model, and then increasing their interaction, their multiplication by 1 unit, and then how much the Y or response changes. Another thing that R gives you is the multiple R squared and adjusted R squared. This metric gives you tells you that how much of the variability of the response was explained by the variabilities of the data. So here it tells you that 82% of the variability of V1, or my response here, was explained using these variables. So this is actually great. The difference between adjusted R squared and multiple R squared is that the adjusted R squared accounts for the number of variables in the model. So for example, if you have another model with 10 more variables, you can compare their adjusted R squares and see which one is bigger or smaller, but you cannot compare their multiple R squares, because multiple R squared always increases when you add variables, because always you can better explain the variabilities into the response if you have more variables, but it doesn't mean that your model is actually good. Okay. As I said before, another way to build a regression model is the Lasso regression. This is very famous. That's why I'm including it here. And so before, what we had was the loss function for the linear regression, which didn't have this penalty into it, and it was only minimizing the squared error between the actual response and the response you predicted using those betas. Okay, how much time do I have? Okay, and now you have this lambda times beta to actually add a penalty to the loss function. You can build this model using glmnet package, and we're going to talk about it later. Okay, now classification is not that much different from linear regression. The only difference is that since the y value here is not, you don't need to actually predict the y because it only takes different integer values. You only need to predict the probability that y takes either of these values. So for example, for a binomial distribution where you only have either 0 or 1 for your y, you can only predict the probability that y becomes 1. And you can use that using generalized linear models, and it converts the y using this link function g, which is a logit function, and it builds the same model for you. Okay, let's move on. I'm gonna explain these evaluations later into the code because we're late. I'm also gonna explain the classification trees there. Okay, let's move to the code now. Let's see, I'm gonna stop the share. So if you have your R Studios open, that would be great. I'm gonna open the.
Kimia, I have a question while you're opening the file.
Yeah, go ahead.
I have it from the beginning of the
I'm sorry.
tutorial. No problem. Is there any way to read a large set of data in chunk? I mean, like in the pandas package in Python, you read some part of the data, like, for example, 1,000 first row of the data, and then in the next iteration, you read the next 1,000 rows of the data.
Yes.
Is there any way?
Yes. This. So that freed package I said, the freed command I said it has another input that you can change that says how many rows, and it computes the number of rows from the beginning, and you can read different kinds of rows, different sets of rows if you wanted to.
Okay, thank you.
Sure. Okay, so this is my R, and if you open the code I put in the Google Drive, does everyone have the Google Drive? Okay, so you can see the code in your computer too, and I want you to, because I deleted some part of the code on purpose, so you can fill it in when we go through the code. Okay, now the very first command, as we talked about, was checking if you have all the packages installed, and then load the packages. So whenever I click the run, you can see the console starts running the codes, and each package that is loaded into R, you can see their description into the console. Okay, next, you need to change this address that I put. This is the address inside my computer. So wherever you downloaded the data, you need to put this the address to the data file here into setwd. This changed the directory of the R to those to the file that you have the data in. So I give you a few seconds.
Hey, I do have a question about when you're loading the packages.
Okay.
Like, how do you, other than it going down there, I think I'm doing it too quick. Like, will it still run in the background, or if I interrupt it, it's just not going to load them correctly? Like, you just have to wait for the loading stuff to come up?
So yes, because it's probably because you don't have these packages installed and they're installing them. That's why it takes a lot of time. Is that why?
No, I do have them installed. I think I'm just doing, I'll do it real quick and then I move on to my next line in the script.
Okay. Then what happened?
I was just curious. I just don't have, like, I was playing around with something I'm doing now, and it didn't ever pop up Any of
Oh.
the, so does that mean it didn't load
So
correctly, or like,
nothing shows up into your console?
I have like, it'll like basically copy down library, caret, tidyverse and stuff, but it didn't give any of the other stuff. So does that mean it didn't work?
No,
Like
it
you
works.
have the,
It's fine, because if you had already installed them, it doesn't do anything.
okay.
Yeah. We're
Thanks.
gonna see if they worked or not later, when we call functions from these packages, and then we can come back and check them if they weren't loaded. Okay. Okay, so I hope everyone fixed the address on their computer up to now. Then we can run this setwd and change the address. Now, the very first data that we're gonna work on, so we have two data sets for regression. One is crime and the other one is car. And I'm gonna work on crime and you're gonna see what I'm doing, and then I'm gonna give you 2 to 3 minutes to work on the car data yourself. So, okay, I'm gonna read the data into my R using read.csv, because the crime data was a CSV file and everything else inside that file was already ready. So I didn't need to put any other information inside the read.csv. And then using the head function, head of crime, it's going to give me the first 10 rows of the variables. Now, if you look at the first 10 rows, you can see there are a lot of columns that have a lot of NA values. So I already know that there are NA values inside this data. Also, there are a lot of there are a lot of variables that tells me that you need to do a variable selection at the end too. Now, from the UCI, I downloaded this data from the UCI repository. In the UCI page, it said that the first 5 columns were not predictive. So I'm going to remove that. How I'm going to, if you put a minus in the set of columns or rows that you're giving to the data, it's going to remove those indices from that data. So I'm going to say update the crime using deleting minus. C means the vector, so the vector 1, 2, 5. So it basically just removes the 5 columns. Now, I already know the answer of the NENA, but I'm just gonna show you how it works. I'm gonna run NENA and it gives me true. Now, I give you 1 minute to work on the car data. You need to read it in and then check the head of the car data. And also, because this data doesn't have column names, I already put the column name here for you. And you need to update the column names using this command. Okay. I don't think it's gonna take a lot of time. So whenever you are done reading the data, please give me a sign. Okay. So if you check the data, the car data is called auto-mpg.data. So we know that this file is different from the read.csv file that we had above. We need to use another command for it. Okay, so I don't know if you're watching me right now on the screen or not, but so I put the header equals true because I thought the data has the header, and you can see that the very first that the column names right now has values. See, you have, like, for example, I have x 307.0, which means that the very first value of the data was inserted into the column name, which I didn't have any column names. So I need to reread the data and change the header to false to fix this. Okay, now it works. So you can see, since it didn't have any column names, it changed it to V1 to V9. Now, same as before, based on the data description in the data page on the internet, I know that the very last column, which is the car name, this is not informative. So we need to remove the last column. I'm gonna give you a few seconds to run this too. Okay.
Yeah, how do you access the last column? I mean, is there any
what?
way, how do you access the last column? Do you have to know the number of columns in the data to access?
Oh, yes. You either need to know the name of that column, which we know it's car name, or you need to know how many columns there are and select the last column. And you can select the number of columns by the function and call, then the data. For example, car. It gives me 9. So it means the 9th. Then it has 9 columns. Okay. So we can remove the last column using minus and call of car, as we said. Okay. Now, if you want to check the data types, I said you can either use the glimpse or summary function. I'm gonna run the glimpse, and you can see how it works. So it gives you different. It gives you all the variables with their data types. Double is DBL, integer is int, and then CHR is the character, and their values here on the right. Now, I'm gonna give you a few seconds to think about it and see if you need to change some of these data types because they don't make sense. And then when you did, you need to check for the missing values. So if you finished doing this, let me know. Since we are a little running behind the time, I have to move faster a little. Okay. So, okay, I move on. So as you can see here, the horsepower is its data type is said it's to be character, but you can see that it's numeric values. So this doesn't make sense, and you need to change that. So you can change that by calling that that specific column from the car. You can do that either using the same method we did previously by selecting its index inside the brackets, or you can use $sign and then select the column name. So you can say car $sign horsepower. It needs to be numeric. So the function is as dot numeric of the car. There we go. Now, see, it gives you a warning message, says NA values introduced by coercion. That's because the horsepower had NA values in it. So when we check for NA of the car, we can see it's true, and those NA values are inside the horsepower variable. Okay. Now let's look at the data types of the crime. Well, there are a lot of variables here in the crime, but we can see there are a lot of NA values too. And I checked this, and there are no like inconsistencies about a variable being character and it needs to be numeric or something like that. Now, to find out which columns are actually having, to find out how many NA values each column has, you can use the function colsums, and then inside the colsums, you can say is.NA of the crime, which gives you a binary matrix, and then the colsums is going to compute the column sums of that. And then you can see which of these column sums were actually positive by saying select those column sums inside bracket that were positive. Okay. Now I see a list of them. You can see that there are some variables like this one. I can't even read it. That has like 1,800 missing values, and the number of rows is around 2,200. So most of those columns are actually, most of those rows for that column was actually missing. So I don't think that column is going to be very helpful for us because a lot of missing values are there. I'm gonna remove those columns entirely. So I'm gonna use select and then exclamation point, which is the not operator in R, and then the names of those column sums that were greater than 1,500. Now this dplyr double colons is telling R to use the function select from this package, because there were two different select functions from different packages. That was giving me an error before. So I had to tell R explicitly to use the select function from the dplyr package. Now, so we can do this, and you can see that the number of columns from 140, it reduced to 120. Also, I'm gonna remove, so the response variable for the crime data is the violent crimes per population. So I'm gonna remove those rows that they have missing response, because that's not gonna help me either in modeling or predicting. So I'm gonna remove them. Okay. Now that we have get rid of the, okay, question, let's see. Oh, sure. Let's see how much is it better, Ganesh?
Yeah, if possible, can you move it a little bit more?
To the right?
Yes, yes.
Okay.
Anyways, those things we don't see much, right, on the right side. So.
Oh yes, yeah. You don't need anything on the right side yet. Is this good? Okay.
Yeah, it's good now. Good now.
Great.
Thank you.
Sure. So now, after we remove those columns, I'm going to check again the column names for those that have any missing values and see what to do with the rest of the variables that have missing. This is basically says that if you look at the functions, you can understand what is going on. The very inner function is computing the is NA of the crime. The next function is computing the column sums for it. And then the which function is going to give me the indices of those column sums that were positive. And the last function gives me the names of those indices. So I can run the misnames, and then if you want to see the miss underscore names, you can see them by calling it. So you can see these values still have missing values. Sorry, these variables. Now I'm gonna replace the missing values inside each of these columns with the average of the whole column. So what we need to do is to tell for each of the columns inside these missing names, we're going to replace those rows that were missing from that specific column with the average mean, the mean function of that column, which is crime underscore, sorry, bracket, comma, then the column name. And we need, this is a must, you need to tell the R to put na.remove equals true inside the mean function, because if you don't, the mean function is going to return na if you don't have if you have any NA values inside that column. The mean function is going to return NA unless you tell it that to remove the NA values. So we can run this, and then we can check the NAs inside the crime, and we see we're good. Yay. Okay. Now you can do the same thing for the car data. I'm going to give you 1 minute to do that. It's very simple. So you need to find out which columns are missing, that they have missing values. And then for those columns, you need to update the missing values with the average of the total column. Okay, so we're gonna repeat the exact same thing and run this for the car data too, and then check if there are any missing values for the car, not cat. Okay, and you see that is false, so we're good. All right, we did this already. Okay, so the next, so we don't have any categorical data for either crime or car, so we're gonna move past this part, but we will have categorical variables for the classification model, so we get that, we get there. So we need to check the near zero variance for the crime. I changed the unique cut to 5 to make sure if there are any imbalanced data, I counted for them. And when you run this, it returns you integer 0, which means there are no near zero variance columns inside crime. You can run the same thing for car. I'm gonna copy this same function. And again, since the data is really nice here, they don't have any near zero variance either. Okay, now the next we're going to, I need to do this because I'm gonna plot a graph here. Next, we're going to compute the correlation of the crime data using the core function, as I mentioned in the slides, and then using the library core plot. So if you don't have this library, if you run it and you don't have it, the R gives you a warning saying there's no package name core plot. You need to run install.packages and then into the quotation core plot inside your console or your editor to install the package and then run this library. Okay, and then this function core plot from the same package takes in the correlation matrix, and these are other inputs that I gave it. It's this tl.col means the color of the text to be black, and the order to be h-cross. This means that it clusters the variables into each other. The order into a cluster way to make sure that it looks nice. And then the position n means nothing and no position here because we don't want to show the column names because we have a lot of variables. Okay, now this is what a correlation heat map looks like. You can see that it's not very clear, but it gives you an idea that there are some highly correlated variables inside the data. You can see these very dark blues here. This means that almost these values are almost the same. So you don't need all of them here. Also, there are some very dark red. That means that they are actually the exact opposite of each other. So we need to evaluate these high correlation more. For that, I wrote a function here. I'm going to go through each step so you can see what I'm doing. So you can write a function in R using the function command. And the function that I've written, it takes in the data and the threshold. So what it does is that it finds out which indices of the data has the data that it takes in is the correlation matrix. So it checks which indices of the correlation matrix have actually their absolute value is greater than the threshold, and they're not 1 because we know that the diagonal elements of the correlation matrix are actually 1s. So if you don't put this and not 1, it's going to return you all the columns you have. So it's not helpful. So we have to tell it not being equal to 1. Oopsie, what did I do? And also being greater than threshold. Now, it takes in, it computes this list of the variables, and then it says if we have any such variables that have correlation greater than threshold, return the name of them. Otherwise, return NA. Now, we can run this function using core_check. This is the name of the function. And the threshold I'm using is 0.95. Okay, so this is the hard part. So you need to actually go through the data and see what are these variables that are highly correlated with each other. For example, this is the list of the variables. Now, if you want to see them exactly, you can see them in another heat map. Okay, so if you look at this huge block of the blue, dark blue squares, you can see that they are very highly correlated with population. So, for example, the number of assaults or auto thefts or I don't know, number of urban living in an area, they are very highly correlated with population. They're all in the same category. They're all the number, they are computed with the number of people living in that area. So they are not helpful because they have very high correlation with population, and then they're going to make the matrix inversion for us really difficult. So one way to deal with them is to create another variable, which is, for example, assaults per population, and then compute the ratio between the assaults and the population and return that and use that variable instead of these. So yeah, but since I already tried that, I tried to create those variables, and then I saw that the data itself had those variables in it. So here I'm going to check if the per population were, so there were any variables that had per population in their names. And I'm gonna check that using these 2 lines. This is gonna give me, you can see that all of these crimes, they have already the per population variable inside the data. So I didn't need to recreate those variables, but if we didn't have these in the data, you needed to recreate them. And so I can remove these variables because I already have their per population ones, okay? Another thing to remove and to check is that, for example, there are a lot of pairs. You can see, for example, a percentage of the families with 2 parents, percentage of the kids with 2 parents. They're basically the same variable. So they're very highly correlated. So you don't need both of them into data. So you can remove one of them. Also, for example, percentage of the persons who own something and percentage of the households who own something. Okay, so they are exactly the same again. So you don't need both of them. That goes on for almost every one of them. So I remove for each pair, I remove one of them to make sure that the data is not highly correlated. Okay. Now, that we remove those variables, we can check the correlation again and see what variables have high correlation. NA. So we are good. Let me make sure that I didn't make any mistake here. So what I'm doing in the to remove underscore crime is that I'm selecting those names inside the crime high correlation that I created here up here. I'm selecting those names that I said from their list. Yeah, so we're good. You can disregard this because here I was trying to compute. Oh, okay, I see what I've done. I just remembered. Okay, so another thing that I checked is because I went down and modeled and then I got NAs and then I had to come back and see what was wrong with the data. So that's why I knew that this part, but you wouldn't know this without going to modeling first and then coming back. One thing to look at is that if you take a look at the correlation for those variables that had per population in them, this is another way to plot the correlations, by the way. You can see that there are murder per population, rapes per population, robbery, assault, burglary, larceny, auto theft, arsons. And if you sum all of them, it would be exactly equal to our response variable, which is violent crimes per population. So this tells us that they actually don't give us any information other than the same response. So I had to remove them to check that they actually their sum is going to be the same as the response for us. I created another column called sum crimes and then created their core plot again. Now, if you can see the sum crimes and the violent crimes per population, they're actually very similar, very, very similar. So that's why I am removing all of those different crimes per population and only keeping the violent crimes per population. If you don't do that and go ahead with the modeling, you will see some errors popping up here and there saying they have like NA values created because it couldn't inverse the matrix. It would be singular, they will be correlated with each other. So that's why we need to do that. Okay. Now, for the car data, one thing I couldn't do for the crime data that we can do for the car is that for the crime data, since there are a lot of variables, I couldn't create the scatter plots that are paired with each other for that variable, for that data set, because it was huge. But we can do this for car. The command to build that plot is ggpairs. It's a very nice plot, I think. I mean, I really like it. It's going to take a little time too. But this is really nice, especially if you're writing a report. You can put it there and you can analyze the data and see what are the values and what are the relationships. But it can only be done if you have limited variables, because this is a huge plot. One thing to notice for this data is that there are some nonlinear relationships between MPG, which is our response, mile per gallon, and for example, displacement, horsepower, and weight. You can see there are like some nonlinear relationship, which would be a good idea. Which would be a good idea to add those square terms, or perhaps 1 over horsepower term into the model right now. You can use that using the pipe operator and the muted function. I have an empty space here if you wanted to add it in. And you can build the model using those. Just remember, whenever you're adding polynomial versions of the variable, you need to normalize them. So you need to subtract the mean from them. Okay, so I was told that I took so long and we are running out of time. So because I don't want you guys to actually, I want you guys to actually see a classification model too.
Yeah, can we save the classification model for another session?
Yes, sure. I can complete the LM models here right now, and then we can do classification later.
Okay, great.
Yeah. So I'm gonna skip the variable selection that I've done here. You can go through the code here and see how I did it. It's not actually hard to read through them, but after I did the variable selection, assuming that it's all done, let me run it. Just run it. Okay. So assuming that the variable selection is all done and we're good with the correct variables into the model, we can run the linear model using the LM function, as I said. And to check the assumptions, you can use the plot LM model. And okay, yeah. And this par MF row equals C of 2 and 2 means that create a 2 by 2 matrix of plots for me. So I'm gonna run this, and you can see how those 4 assumptions can be checked here. The fitted values versus residuals is the very top left, and you can see that there are some variance concerns here. We can deal with that by changing the variables, but let's move on and assume that it's good to go. And yeah, and also, as I said before, you can yes, you can also create the plot of the true values versus the predicted. And if you're writing the paper or writing the report and you want a beautiful plot of the estimation for each parameter, you can use the SJ plot package, and then you can use the LM tab_model, and this gives you this cute table if you wanted to use it in your reports. I'm gonna stop here, but you can go through the comments I have inside the code and see how I do the prediction. Because for the prediction, you cannot use all of the data at the beginning and build a model. You need to actually split the data into training and modeling and then work with that.
Yes, thank you, Kimia. Thank you very much for your discussion
Sure.
of our data science.